What if I told you satellites are constantly falling but never hitting the ground? Have you ever pondered why satellites, those marvels of modern technology, don't fall out of the sky? It's a question that has likely crossed your mind, whether you're gazing up at the night sky or simply using your GPS to navigate to the nearest coffee shop. The answer lies in a fundamental force that we all experience every day: gravity. Gravity, as you likely know, is the force that pulls objects towards the center of the Earth. Every time you jump, it's gravity that brings you back down. But what happens when we're talking about objects that are thousands of kilometers above the Earth's surface, like satellites? Here's where we need to bring in some other key concepts, starting with Sir Isaac Newton's laws of motion. These laws, established in the 17th century, still hold true today. They tell us that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by a force. This tendency of an object to keep doing what it's doing is called inertia. Now let's apply these ideas to a satellite. A satellite is launched into space with a huge amount of speed, enough to overcome Earth's gravitational pull. Once in space, it continues to move forward due to its inertia. At the same time, Earth's gravity is constantly pulling it towards the center of the Earth. This creates a delicate balance. The satellite is always falling towards the Earth, but its forward motion, or inertia, keeps it from crashing into our planet. Instead, it falls around the Earth, in a path we call an orbit. This is a dance governed by forces we can't see, but are always at work. The gravitational pull that keeps the satellite falling, the inertia that keeps it moving forward, and the centripetal force that keeps it moving in a curved path around the Earth. So, it's not that satellites don't fall, they're actually falling all the time, but why don't they crash into Earth? Imagine throwing a ball so hard it keeps missing the Earth as it falls, and you'll start to grasp the concept of an orbit. This is the grand leap of imagination we're going to take as we plunge into the world of satellites. So, let's say you've built your satellite, a marvel of modern engineering, and now you want to launch it into space. It's not as simple as just pointing it upwards and saying, "Go." You need velocity, lots of it. Now, why is that? Well, imagine tossing a ball. The harder you throw it, the further it goes before gravity pulls it back down. But what if you could throw that ball so hard that, while it was still falling towards the ground, the Earth curved away beneath it? That's how an orbit works. The satellite is continuously falling towards the Earth, but its forward motion is so great that it keeps missing it. This is a delicate balancing act, a tightrope walk between momentum and gravity. The satellite's forward motion wants to take it in a straight line, while gravity is constantly trying to pull it down. If the satellite moves too slowly, gravity wins and it falls back to Earth. Move too quickly and it will escape Earth's gravitational pull, shooting off into the vast expanse of space. But get the balance just right, and you've achieved orbit. The satellite is now in a continual state of free fall around the Earth, perpetually plummeting but never hitting the ground. It's a bit like falling over the horizon over and over again. It's this intricate dance, this tussle between momentum and gravity, that allows us to have satellites orbiting our planet. They provide us with a host of benefits, from weather forecasting and GPS navigation to international communications and scientific research. So next time you check the weather on your phone, spare a thought for the satellite that's falling around the Earth over and over again in a perfect balance of speed and gravity. This delicate balance is what keeps our satellites from plummeting back to Earth. The height at which a satellite orbits also plays a crucial role in its ability to stay aloft. This is where the fascinating concept of altitude comes into play. Now let's take a moment to consider the Earth's atmosphere. This isn't just a simple uniform layer of gas. Instead, it's a complex structure divided into several layers. Starting from the surface, we have the troposphere, stratosphere, mesosphere, thermosphere, and finally, the exosphere. Each of these layers has its own unique characteristics, and they all play a role in how a satellite orbits our planet. Let's dig a little deeper into the thermosphere and exosphere, the two layers where most satellites reside. The thermosphere, despite its name, is actually quite cold. However, it's also very thin, meaning that there's little air resistance. This is a good thing for satellites because it allows them to maintain their altitude without using too much energy. On the other hand, the exosphere is the outermost layer of our atmosphere, where molecules of gas are so sparse that they can escape into space. It's in this layer that geostationary satellites orbit, maintaining a constant position relative to the Earth's surface. Now, here's an interesting fact. Satellites in low Earth orbit, or LEO, have to travel at incredibly high speeds to resist the pull of gravity. We're talking speeds of approximately 17,500 miles per hour. Can you imagine? At these speeds, they can orbit the Earth in a mere 90 minutes. However, as we go higher into the Earth's atmospheric layers, the gravitational pull decreases. This means that satellites can afford to slow down a bit. For instance, those in geostationary orbit, which is much higher than LEO, travel at a relatively leisurely speed of about 7,000 miles per hour. This brings us to a key insight. Altitude and orbital speed are inextricably linked. The higher the satellite's altitude, the lower the speed it needs to maintain its orbit. And this is why altitude plays such a critical role in keeping satellites in the sky. So, the higher the altitude, the slower the required orbital speed. And that, my friends, is the magic of astrophysics. But what about atmospheric drag? Doesn't that pose a threat to our satellites? Indeed it does. Atmospheric drag is the resistance experienced by an object as it moves through the atmosphere. Picture it like trying to walk through a pool of water. The water provides resistance, slowing you down. In the same way, the thin veil of atmosphere remaining at the altitudes where satellites orbit provides a subtle but persistent form of resistance. This atmospheric drag can decrease a satellite's speed, causing it to lose altitude over time, a process known as orbital decay. As the satellite dips lower and lower, the atmosphere becomes denser, increasing the drag and accelerating the decay. If left unchecked, this could eventually cause the satellite to plummet back to Earth. But worry not, we've got this covered. To counteract the impact of atmospheric drag, satellites are equipped with propulsion systems. When a satellite begins to drop too low, a maneuver known as a reboost is performed. The satellite fires its engines, pushing it back up to its proper altitude. However, the fuel for these maneuvers is finite. Once it's gone, it's gone. That's why engineers are constantly seeking ways to make satellites more efficient, to extend their operational lives as much as possible. Innovations like electric propulsion systems promise to make our satellites even more resilient to the effects of atmospheric drag. There's also the practice of drag makeup maneuver, where satellites are initially placed in slightly higher orbits. As drag gradually pulls them down, they naturally settle into their operational orbits. This proactive approach can extend a satellite's life by several years. So while atmospheric drag is a threat, it's not one we're helpless against. With a combination of smart engineering and proactive strategies, we've found ways to keep our satellites soaring high, ensuring they continue to play their vital roles in communication, weather monitoring, navigation, and so much more. So, while atmospheric drag is a concern, it's one we've learned to manage. In the grand cosmic ballet, satellites dance a delicate balance between falling and missing the Earth. Let's take a moment to revisit the celestial choreography we've just unfolded. The first principle we discussed was gravity. This fundamental force of the universe, an invisible hand, acts as the lead in this dance, pulling the satellites towards Earth. However, it's not a one-way street. Simultaneously, the satellite's forward motion, its momentum, is trying to carry it in a straight line away from Earth. This is where the concept of the perpetual plunge comes into play. It's a seemingly endless fall where the satellite constantly misses the Earth due to its speed. The satellite is falling towards Earth, but also moving forward fast enough to miss it, creating a cycle that we observe as an orbit. Now, the altitude at which this dance takes place is of utmost importance. The higher the altitude, the slower the satellite needs to move to stay in orbit. At lower altitudes, the satellite has to move faster to resist the stronger pull of gravity. It's like adjusting the tempo of the dance to the music. But what's a dance without a little drama? Enter atmospheric drag. This is the friction between the satellite and the wisps of atmosphere at these altitudes. It's like a subtle gust of wind trying to disrupt our dancers. However, with the right speed and altitude, the satellites can overcome this threat and maintain their orbits. All these elements interplay in a complex but fascinating dance that keeps satellites in their orbits. They are falling yet not falling, moving yet seemingly still. This dance is a testament to our understanding of physics, our mastery of technology, and our unending curiosity about the universe. It's a complex dance, but one that we've mastered, allowing us to keep our eyes in the sky, exploring the cosmos, and enhancing our lives.